Oh, okay. Hi, everyone. My name is Anantaa Kotal. I'm a PhD student at University of Maryland, Baltimore County. And today I'm going to be... sorry. So I have, hold on. I think I can, yeah. Okay, good. Yeah, sorry about that. Okay, yeah. So so today I'll be presenting our paper, PriveTAB, Secure and Privacy Preserving Sharing of Tabular Data. So in the past decade, we have seen a huge evolution in the data landscape. So we as a community are increasingly becoming more dependent on tech. What this means is that we have this data has been collected about different different parts of our life at various stages. We have more data on things like online behavior, medical information, and even things like your shopping preferences. We also have like efficient data collection systems now that can collect and curate these huge amounts of data and store them in a meaningful way. We also have advanced data storage systems, which we didn't have before, which can actually keep this data and make them useful for us. So what does this mean? Can we actually use this data? So we have very powerful machine learning systems now that can actually consume this data and gain meaningful information from it. So we do have the technical capabilities to use this data. The thing is, like, can we actually use it in practicality? And the short answer is no. Because most of the organizations, private or government, that collect this data have an obligation to their customers or consumers to protect their privacy. So they really can't give us their data for public use or even analysis, even though they contain like a wealth of information. So for example, SOD, or Security on Demand, is a company that monitors and analyzes customer network activities. So here is a diagram that basically shows how SOD monitors and collects data on the customer computer and watches and analyzes all the alerts and logs. So obviously, this is like it collects a lot of data from millions of its customers, and it is very useful for any kind of security data analyst, especially for things like intrusion detection. It can give very valuable information that would otherwise not be available for analysts. The thing is, SOD again has an obligation towards its customers. So it cannot really make its data public for use for security data analysis. But SOD did release part of its data, a modified version of its data, as a part of the IEEE Big Data 2019 Cup. And what we saw from this challenge is the contribution that data like this can have on on algorithms that can analyze and look out for or improve alert systems. So really, any data like this will be extremely useful for data analysts, but it's extremely hard to encourage them to share their data with us.
Hello, Ananta. I'm sorry for disturbing you. This is Nitesh from online. I think your slideshow is frozen because people online are stuck at slide 3.
All right, let me see.
Sorry for that.
Can you see it now?
Yep, we are on slide 4, so you can see it. Thank you.
Thank you. Yeah. Yeah, so how do we encourage organizations like SOD to release their data for our use? Obviously, they can't release the information they actually do collect, but we now have like data privatization algorithms that can actually manipulate this data and share a version of it that protects privacy information while still making it useful for data analysis. So one of the most popular ways of data privatization is data anonymization, which basically protects private information by hiding or encrypting identifiers that can be used to link an individual to the stored data. So say a participant is part of a study, we hide enough information from that study or encrypt it so that that participant cannot be re-identified just from that data. But there are certain issues with data anonymization. So one of the most popular techniques of anonymization is generalization, where you basically hide or generalize part of the data points so that the data rows becomes same as at least like one or more data rows in that data set. The problem with that is to actually have sufficient privatization through that, we have to generalize or hide quite a bit of the information in the data rows. And this can lead to low statistical performances in data analysis. The other popular way is to add random noise or perturb the data in certain ways. It can be useful, but the problem is like with categorical data, if you add random noise to it, it can change the categorical values in certain ways that basically makes the data points substantially different from what it was in the original data set. The other technique is to do data anonymization through data generation. What it basically does is creates an entirely new data set from the original and uses.
Sorry for disturbing again.
Yeah.
I think it's still on slide 4 for the online viewers.
Okay, let me see
Sorry.
again.
Yeah.
Yeah, that's what I did. Yeah, I think the people online might see my presenter view, but like I had to share the desktop version of it. Hopefully it will be better now.
Yep.
Thank you. Go back and forth, one slide or back.
Yeah, okay, sure.
Yes, I see another slide now, thanks.
Yeah, okay. Right, so we were talking about data generation. As I said, like we are going to replace, we can replace the entire data set with synthetic data. So the benefit of that is like, since it's all completely fake, it cannot be linked to, it cannot be re-identified to real participants. And if we can create a fake data set that is like that has similarities and properties to the original, it can contain very realistic information and can be used for data analysis instead of the original data set. So one of the most popular ways for data generation is using generative adversarial networks. So without going too much into the details, it basically has two models which learn against each other. So we have the generator that tries to generate new samples and the discriminator model that tries to distinguish between samples that the generator has generated and real samples from the data set. So through consecutive iterations, they both get better, and generator starts generating samples that look very close to what an original sample would look like. But there are certain challenges with generating tabular data through typical GANs. So one of the features of tabular data is that it contains a mix of discrete and continuous variables. They are basically non-Gaussian distributions. So you cannot use typical GANs that are used for like images and data like that to generate tabular data. Also, the population in the discrete columns, they can be imbalanced, and that is actually one of the features of that data set. And it's not something like typical GANs can maintain. So it's something that we need to take into consideration. And thirdly, the continuous columns in the tabular data, they can have multiple modes. So that's also something we need to keep in mind. So one of the strategies to generate tabular data is using conditional GANs. So again, like I'll go, so there are the two most salient features that make conditional GANs more powerful to generate tabular data is the conditional generator and the training by sampling. So basically, the conditional generator in conditional GANs, instead of generating entirely new data points, it actually generates data points given the condition that a discrete, like one of the discrete variables has a constant value. And through training by sampling, this network tries to minimize the distance between the sample data, between a sample data and a generated sample for the same constant value of the discrete variable. So if we were to look at this model of a conditional GAN, so basically instead of a discriminator, we have a critic model, and the generator, it tries to generate a sample given the condition that given the condition that one of the discrete values has been is constant, right? So it tries to generate the rest of the data points, the rest of the variables for that data row. And then we take another, take a sample from the original data where the same discrete value is constant, right? And then the critique model, it takes the distance between these two sample points, the generated sample and the original. And this distance now becomes the loss measure for the critique and the generator. So this gives us more realistic values for the tabular data. And it's one of the things that we can use to create a data set, right? So if we train conditional GAN, both the critique and the generator with the real data, and use the generator to sample data points, we can create a synthetic tabular data set. But there are certain limitations of just using conditional GANs to create a synthetic data set. Suppose like our original data looks something like this, where we have three participants, Alice, Alex, and Bob. And if we were to randomly generate samples from the generator, the synthetic data might look something like this. So it has introduced small changes into the attribute values, such that like all of the data points here in the synthetic data do not actually appear in the original data. So that's fine, but the problem is like here we have repetition, some of the attribute values appear more often, but we actually completely miss out on some of the other attribute values. So this is not actually an accurate representation of the original data set. And we need to, we have introduced changes, but we have skipped some of the attribute values. So we actually need a better way to generate samples from the generator in the conditional GAN. So to summarize, basically, like we need some way to create a more accurate representation of the population diversity in the original data, population diversity of the attributes in the original data set, and transfer it to the synthetic data that we are creating. So just to look back quickly at one of the data anonymization techniques, we had t-closeness, which basically said that like for a set to be t-close, the distance between the distribution of its of all of its attributes, all of its sensitive attributes, had to be within a certain distance from the distribution of that attribute in the whole table. So taking cue from it, if we were to maintain consistency of like representational consistency of the attributes in the synthetic data, we actually have to bring down the distance of these, the distribution of the attributes in the actual and the generated table. And if we can do that, this would ensure that there is adequate representation of all attribute values in the generated data set. So with that in mind, we add another step to the sampling part of the conditional GAN. So we calculate all of the EMD for the attributes in the generated and the original data set. And we take the maximum value of it. And as long as the maximum value is above a certain threshold, we keep on sampling from the generator. And once all of the attribute values are below that threshold, we can stop sampling, and we have a version of a synthetic data set that can accurately represent and replace the original data. So for the network event data that we have from SOD, this is what the sampling process looked like. So at the start, we at about 10,000 samples taken from the generator, the maximum EMD was quite high, and we brought it down to 0.6, and that's the point where we stopped sampling. So now we have this generated data, but there's still a problem in sharing it publicly. So basically, like GAN is generating new data points, but it can only generate discrete values that have already appeared in the original data set. What it means is like it cannot actually create its own strings or create its own discrete values, right? So, and the problem with that is some of the strings itself can be private or sensitive in the original data set. Like for example, with the SOD data, it was the alert ID, right? So we cannot actually share the actual alert ID in our public data set. So we need some way to hide it. And it's pretty easy to do that for strings, because like the specific value of the string is not relevant to our analysis. So it can be replaced with any pseudonym mechanism, as long as there's a one-to-one translation. So in our model, we have used just the SHA encryption technique to get an encryption for all of the strings that were sensitive. So after for the network event data taken from the SOD, these are the real samples, and then our generated tables look something like this. So there are we have introduced small changes in the discrete values such that it is substantially different. Such that it is not part of the original data set, so it's not leaking any kind of information. But it is still essentially, it still has the same properties as the original data set, so that it can still have it can still be utilized to perform the same kind of data analysis as we could have done in the original data set. So to evaluate how good our synthetic data set is, the basic objective is that it should be able to replace the original data for any kind of machine learning task. So for the SOD data, the task was to identify attack events. So if the real data, if any machine learning trained on the real data said that XYZ is an attack event, then then any machine learning model trained on the fake data should also say that XYZ is an attack event. So with that in mind, this was our evaluation model. So we separated the original data into a training and a test set, and we also used the original data to create our own synthetic data set. So we have the first ML model, which was trained on a set of the original data and tested on a set of the original data. And a second model, which was trained solely on the synthetic training data set, but tested on the test set taken from the original data. So the accuracy for the first ML model is our baseline accuracy, and the accuracy for the second ML model is the accuracy we can gain from the synthetic data set. For this evaluation on the network event data taken from SOD, this is what the result looks like. So basically the baseline accuracy, baseline AUC score is 0.92. And for the classified chain trained solely on the generated data, it's 0.91. So it's pretty close. There is very minimal loss in information. So we can use the generated data in place of the original data. We also tested on a couple of other tabular data sets. So the green bars are basically the baseline accuracy, and the blue bars are the accuracy when trained on the synthetic data. And as you can see, like there is very minimal loss in accuracy when the classifiers are trained on the synthetic data. To summarize, like there is still a huge gap between the computational capabilities of modern machine learning models and the data that is actually available for use publicly. Hopefully, like efficient methods of data privatization can bridge this gap, can encourage private and government organizations to release their data for public use. So our experiments have shown that synthetically generated data can be analytically similar to original data and basically replace them for learning tasks. And we hope that this would encourage the organizations to release their data, which can be really, really helpful for academic research. Thank you, and I'm open to questions.
That resides with the classifier.
Sure.
Yeah, this one. So which classifiers are we talking about?
Okay. Yeah, so we tested with a couple of them. So basically, this was part of the IEEE challenge, right? And they had a winner. So we did not have the winning classifier, but like we took some of their ideas and created our own. So it was a variation on the XGBoost model. I think there was like k-stratified sampling with XGBoost. So yeah, that was basically the classifier we used here. I think we tried a couple of them, a couple of the other ones, like the second winner. I think they used an LSTM, but I think it was in the part of the original challenge. They noted that like XGBoost is actually the best classifier for this data.
Right, but what I was wondering was how much the difference is between second classifier as a baseline and then grade one. Maybe it doesn't do well as the first one, but what is the
right? Yeah, that's a good question. I don't remember the score for this specific data set, but for the other ones like this one, I think like we ended up using the scores for XGBoost as well. But we did try with a couple of other classifiers like the like starting from logistic regression to the CNNs and everything. And they were also pretty close, like around like this graph is pretty typical of what the scores look like.
I personally also have a question. Can you go back to the actual results? The results, yeah, like this. So you are here comparing the baseline classifier trained on original data and the classifier trained on generated data, and it's given you pretty much a close range of results. My question is that this table, is it reflecting the same classifier? Are you comparing the same classifier here, or
yes, no, the model is same. It's just trained on different data sets.
The thing is that when you go back to your the slide before, you have two ML model 1 and ML model 2, which kind of confused me if the results were coming from the same
right. So the hyperparameters are the same, but like I said like two different models because they are actually trained on two different data sets. So
can we see if online we have any questions online?
Yes, I had a question if you can hear me.
Yeah, please go on.
Go on.
Yes, thank you. Interesting work. So another dimension that might be missing is how far are the synthetic data from original data? You might need another access to how much privacy preserving or distance they are to the original data, and then whether and of course there's a trade-off, right? The accuracy of the model trained then would probably get ahead as you get farther from the original data. As long as the various privacy considerations are met, maybe that's okay. But I thought, yeah, you probably need another dimension of evaluation too.
Yeah, that's a good question. And like, so this metric determining like how far synthetic data sets are from the actual data and how far it is in terms of utility is like, it is completely a study on its own. Like a lot of people are working on it, trying to figure out how we could adequately measure this different data sets and compare them.
Yes.
But like what I would say, so like obviously there are a couple of other things that we could try, but I would also say like the distance measure for the attribute values in itself is also a measure of how far the synthetic data sets are from the original data. So since we have brought since our maximum EMD is below 0.6, what this means is like for each of the attribute, the distribution is no more than 0.6 in distance from the distribution of the attributes in the original data set.
Yeah, I see. Yeah. As you said, it's a line of research. It's a whole new line of research for that aspect too. Yes. Yes, both minimum and maximum. It should be close enough, but should be different enough. Like each row should have maybe no identical rows, or even no values in a row should be identical to original if you want different. But also, of course, not too different, because then you want your models to be learning the same thing. So yeah, there are these. I think there's a trade-off there. Thanks.
One last question I had in mind. So you have synthetic data and original data. How large were each one of them, like the original data and synthetic data, and also the relation between those two? Like what's the ratio between how much synthetic data you produced compared to the original data? Because if you feed in that through the model, is it the same training data proportion that you gave to the first model compared to the synthetic data that you have?
So what we saw was like it depends on the original data set. So like for the network event data, I think the synthetic data set was just below twice the size of the original data set. But for others, like for the other tabular data sets that we experimented on, so like with the IRIS data set, it actually had to be 5 times the size of the original data. But for others like census income and the credit approval, it was almost like a 1-to-1 ratio between the size of the original and the train.
Just because when you're training with much more data, that also makes the model has more complexity in terms of the training and time of the training.
Yeah.
So also like comparing those two models maybe should be another like processing step or enhancing the data, the large data that you have before feeding it to the model.
Right. Yeah.
So why does the size vary so much?
So basically, so when we are trying to bring down the threshold to 0.6, we don't stop sampling till we have that. So yeah.